Okay, last section. So 9.6, we don't spend a whole lot of time here. Again, this is just one page, and I'm going to be writing down some stuff, but ultimately, if you want to get a better idea, that you can go ahead and read. So real gases in the real world, things don't behave as ideally as one wants. So real gases, when they are not behaving ideally, there are a couple of circumstances where you're going to run into that. So first and foremost, real gases do not behave ideally at high pressures. So here we have, I've got to come up with a better graph for this, but what we see is the value of PV over RT, which is actually what we call the compressibility factor, Z. So Z is equal to PV over RT. This is the compressibility factor. What we see is as we increase the pressure, so this would be ideal behavior. And what we see is at higher pressures, we tend to see that it doesn't matter what the temperature is, it is not on that line. But the truth of the matter is, this is 0, this is 300. So meaning we spend most of our time right here, and they pretty much will behave ideally. We don't really have to worry too much about this, and we'll see this in the end. As temperature increases, it actually helps it behave a little more ideally. But at really low temperatures, we also see this trend of not having this ideal behavior. So in the end, high pressures do not behave ideally at high pressures, and also at decreased temperatures. So real gases occur at high pressures and low temperatures. And there is a reason for this. The closer proximity these molecules are to one another, the more likely they're going to interact with one another. And therefore, once they interact, they're not going to be behaving ideally, because the whole point of a gas behaving ideally, an ideal gas has no interaction with its walls of the container, with other molecules. There's no interaction whatsoever. So that's the real struggle. So ultimately, those are the two deviations, because I guess I should just put this down here, but no, I'll leave it there. That's fine. Real molecules do have volumes and do attract one another. So two assumptions that we made was that, and the last thing actually, that gases is so small in quantity that they actually do not take up any of the space. Well, if we increase the pressure, by increasing the pressure, we are bringing all of those, we're decreasing, or ultimately we're decreasing the volume, right? Because we're bringing those things together, or more importantly, we're just bringing those particles closer and closer together. So when we bring those things closer and closer together, we're causing real behavior. Okay. Also, as we cool it down, we decrease the temperature. We're allowing these things time to interact, because they're not moving as quickly and they're starting to interact with each other. So we're also getting real behavior as well. And so what ends up happening, and intermolecular forces, we're going to talk about it, are just interactions of things. So in ideal circumstance, these things are flying in perfect straight lines. In a non-ideal, in a real circumstance, what you end up with is these things are actually interacting with one another. So if they're interacting with one another, ultimately what you have is, here we go, they're pulling towards each other so if they're interacting right there, what they see is they start to curve towards one another, because they're kind of, when they go by, they're kind of pulling towards one another, and therefore they do no longer have real paths. This brings us to the van der Waals equation. This is the PV equals nRT. Here is my pressure component. Here is my volume component. And you'll notice that they have these two additions. These two additions right here, I guess subtraction in one case, these two additions right here are accounting for changes in behavior. Okay, so this is the important thing. This is kind of the shift, taking into account corrections in attraction and volume of the container. So let's just take a look at this first. So this term right here is taking into account molecular attraction. Corrects for molecular interaction. And this term is going to account for corrects for volume of the molecules. The volume these molecules take up because they're going to behave differently. So a couple of things that we should take a look at. So there's a couple of numbers here. So first of all, N squared over V squared, that's moles and volume. Okay, so moles and volume, because that's going to be important. So moles and volume for the pressure component. Okay. Yeah, why moles and volume? You can imagine that when this term, when the volume is large and the moles are small, that's going to make that completely negligible, right? If I have a very small number of moles and a very large volume, we can now go back to ideal behavior because the volume is actually negligible, right? So volume is large, moles are small. We can essentially ignore this term. We can ignore this term altogether because that's essentially getting us nowhere. The A term, that's kind of new. So A in this case, the A is going to, again, this is just a correction. It's going to correct for the strength of attraction between molecules of a particular gas. So strength of attraction. So again, taking into account intermolecular forces. And the unit for this is liter squared times atmospheres all over moles squared. Why is it that the unit? Because it has to cancel out the other two units that it's with, right? So if I am multiplying A, if I'm plugging in A here, what we're ultimately going to see is mole squared, liter squared, leaving us with a pressure that gets added. So ultimately A cancels out those other two terms and we just end up with pressure. So strength of molecular attraction. B, let's see, B is going to be the measure of the size of the molecules. Okay, so the larger they are, the more contribution that they're going to make, because if they're taking up a bunch of space, again, that's a volume correction. So we have to include that as well. And that unit is, again, same thing, liters per mole. The goal is to just cancel out the mole quantity, because again, that's moles. And we want to cancel that out. And so it just leaves volume plus volume. So liters plus liters. Okay, so just those A and B terms, let's take a look at some values quickly. A, B, so nitrogen is very small and it's not going to interact with anything because it doesn't have any forces that are going to interact. 1.39, small number, 0.0391 for B. And these can be looked up in an appendix. If you actually have to do these corrections, you absolutely can. H2O, it is about the same size. Again, B is for size, and this is interaction. A is interaction. Water is about the same size as nitrogen, or it's tiny as well. So 0.0305. So the size thing is the same, but it is polar. So it interacts a bunch. Water interacts a bunch. It has a much higher value for, the attraction. And then finally, let's look at a really large molecule. It is really large. And so the size factor is 0.1383. And the interaction, it is going to have strong London dispersion forces at 20.4. So again, large size, as we increase the size of it, or molar mass, we increase the value of B. When we increase the interaction, or I'm just going to say intermolecular forces, we're going to see an increase in A. So that's the trend that we see for that. But ultimately, we're not really going to use this a whole lot. I just want to point out the fact that real gases are a thing. They don't behave in very extreme circumstances, low temperatures, because now we're getting towards lower temperatures. They want to become a liquid. And then really small spaces, the volume is now relevant. So we have to take that into account. But ultimately, the calculations you're going to find out are pretty similar to the calculations we would come up with for an ideal gas. Okay, that's it. We're not really going to do any examples on this. It's just something to watch. And that is pretty much it for gases. So yeah, that's pretty much it for gases. We'll do an assessment and we'll move on.